It's a pleasure for me to stay here. I'm Daniel Diaz. I'm from the University of Rosario in Colombia and also from New York University. Well, I will just do a brief introduction of myself. I'm working as, I have a PhD in computer science from the University of Murcia in Spain, working mainly and research mainly in cybersecurity, in IoT, cybersecurity, in social media also, in software. I am an assistant professor, as I said before, in the University of Rosario in Colombia, and a visiting professor in New York University. I've been teaching for 7 years different courses for ethical hacking, security in software, incident handling, and forensics. For example, in this moment, I'm teaching that course. Also, for example, there's artificial intelligence and cybersecurity. And the most important topics that I have been researching the last years are arbitrary intelligence, privacy, and IoT mainly. Yeah, it's a pleasure for me to stay here, and I will give this talk about the application of a new technique that is named the chaos security security engineering in IoT ecosystems. I will, of course, introduce first what's chaos engineering, because it's a new concept that maybe is not common for everyone. So I will introduce that before. And then I will speak about a study case that we have working on in military systems where that can be applied, even if it's not restricted for that kind of systems, can be applied in another system, but the use case that I will present is in that direction. So yeah, just saying that I said before, I'm working in the School of Engineering in the University of Rosario and also the Tandon School of Engineering and the Center of Cybersecurity of New York University. These are my LinkedIn profile and my personal page. If you wanna contact me, it's okay. Well, I'm also the leader of some academies in the university where I work. We have some academies that are a good way to make the students get closer to the industry. So we have academies of Fortinet, Amazon, and Easy Council. All of them, they provide cybersecurity services and cybersecurity certifications. So I'm the leader of that those academies also, and I have another certifications also in cybersecurity. For example, the ethical hacking, the certified information officer, lead auditor. There are also other certifications that there is not here, but I also have those certifications. This is part of the team that is working in this project. Some of them are students from the bachelor. We have a major in applied mathematics and computer science. We have also students, well, not students, but they are researchers from the University of Murcia who are also working in this project. And yeah, we have obtained different products and contributions until now that I will explain to you today. So first, I will speak about what chaos. And I will first start saying that many of us, we think that chaos is something that is not something that we want in our system. It's something that we don't want. But actually, sometimes the chaos can be interesting. And the chaos can be the source of creativity or the source of something that we maybe are not expecting. And maybe the systems need this kind of chaos to discover new vulnerabilities, to discover failures. And yeah, we will use chaos actually to make our systems more resilient. There is a famous phrase of Nora Jones saying that chaos engineering is the practice of introducing or injecting fails in a system to improve its resilience. And this is actually what we'll do today, specifically trying to identify cybersecurity fails. So first, we will define what's security chaos engineering. That is the same concept of chaos, but applied to cybersecurity. So it's identification of cybersecurity control failures with the proactive experimentation to build confidence in the system ability to defend against malicious conditions in production. There are many important words or keywords that I will say that are in this phrase. Maybe one of the most important words is, of course, build confidence, build resilience, right? But the second most important word maybe is in production. We are not speaking here in this, at least in this slide, about systems that are being developed, but systems that are already in production, that are already deployed. So how will we be able to identify vulnerabilities in a system that is already deployed? That will be the, yeah, sure.
So just a general question. So, I mean, in cryptography, people have distortion attack, right?
Yeah.
So what is the difference between chaos engineering and distortion of, I mean, cryptographies that people have been devising in the past? So what's the difference?
Yeah, I have one slide for that.
Sorry?
I have one slide for that where I will explain the difference between this and the traditional perspective.
Okay.
Yeah. Just give me 3 slides and I will explain it. Thank you. So yeah, this was introduced in 2020 by Aaron Reinhardt and Kelly Shortridge. They published a book about security chaos engineering, and when they introduced the concept and they put some examples of what this means. But yeah, we will speak with some example about it. So first, before going deeper to the use case, we need to know how to do it. So there is a methodology to do it. The methodology to apply security chaos engineering is actually based in the scientific method. So what's the scientific method? It's actually 4 steps. The first step, we do the observation of the environment, or in this case, will be the observation of the system. So we identify what do we want to observe. For example, some kind of metrics related with HTTP headers or related with some measures that we want to control in the system. The second step, we define the steady state. The steady state is the normal condition, what should be assumed as normal in a system that is not attacked. Okay. For example, if we are speaking about a web server, we will say, for example, that an HTTP request should have a response time less than 10 milliseconds. Then we define an hypothesis. We say, okay, if the system is properly configured, properly deployed, we should and scale-up configuration. When the system is being attacked by a distributed denial of service, there should be a scale-up config that make the system more resilient and avoid that the system can be unavailable, because that configuration will make the system able to respond to different amounts of requests. So that's our hypothesis. So in the running experiment, we validate the hypothesis. We will validate if actually the auto scale up config will be enabled and will be used. So a bit obvious, but is necessary, because many times when we implement security controls, we don't validate the assumptions. We assume that the security controls works. We assume that the security controls will do their job, but it's not always true. So with this methodology, that is the fundamentals of security chaos engineering, we will introduce to a system that is in production, we will introduce some kind of fails, let's say, or some kind of attacks, so we can validate if the security controls are working properly. So this is actually the backbone of the security chaos engineering. Okay. Okay. So the question is, what you asked before is, okay, so this is nice, interesting, at least interesting, but what's different between this technique or this methodology to validate vulnerabilities in systems and the traditional techniques? Because there are already traditional techniques for doing pen testing and ethical hacking. So what's the difference? There are many differences, and I will explain each one of these differences. Okay. The first one is that in the most common way, or in the most cases, the pen testing and the ethical hacking is offensive oriented. It has an offensive approach when you are assuming that you are a black hat, you have a black hat role, and you are trying to attack the system and try to break vulnerability. Okay. In this case, the security chaos engineering does not only force you to think in an offensive way, but also in a defensive way, because you are part of a blue team, but also the red team. You are like the purple team, because you have the two perspectives, both perspectives, you have both of them. Also, you are not only reviewing vulnerabilities that are already known, you are evaluating assumptions that maybe you are assuming that are working, the security controls that are working, but not working at all. So yeah, that's also another difference, that we are testing here the assumptions, not only the vulnerabilities. The third bullet in this case is the scientific method. When you apply ethical hacking or pen testing, in most cases, if you have done before, for example, for a company or for an organization, what you do is the typical manual work where you launch a vulnerability scanning, a vulnerability scanner, and then you identify the criticity of each of the vulnerabilities that you found, and then you try to exploit using some exploit that kind of vulnerability. In this case, we are using a scientific method that is not based on the vulnerabilities that you find, but in the assumptions that you want to test. You want to test controls that you don't know that they have vulnerabilities, because you will test if they have vulnerabilities. And also, the last point that is maybe the most important one is that you don't implement these kind of techniques only in the deployment phase. You can implement these techniques in the previous phases. For example, if we are speaking about software, in all the phases of the software development life cycle, you can implement this in the development, on the testing, and also, of course, in the production. So it's more complete, I will say. It's a methodology that can be applied in different phases, not only at the end of the solution. So yeah, this is basically the idea. I don't know if I respond to your question partially. Okay, I will try to explain better in the use case, and maybe in the use case will be clearer.
And Daniel,
yeah,
if you compare to the other techniques like fuzzing, is this something similar to fuzzing in software security engineering?
Yeah, has some intersection points with fuzzing. We will speak specifically about the software development cycle later. But yeah, have some like similarities because they're looking the same. They're pursuing the same goal.
So this is like more network oriented, and the other is more software oriented.
Actually, this can be applied in all the layers. You can apply this in a layer of infrastructure, but you can also apply it in the layer of software. It's more transversal, I would say. It can be applied in different layers. Okay. Yeah.
Just a comment also about the cloud engineering. The different functional other options. In fact, what I understood, the main part is really the fact that you introduce intentionally attacks or failures in some other context in a system in production. It's really, for me, it was really the main difference between cloud engineering and the traditional approaches. This is what I understood about cloud engineering in other contexts.
Okay.
Resilience.
The resilience, yeah. Yeah, actually, this concept is being supported by Google, by the site reliability engineering group from Google, because they are using exactly the same concept, but not for security, but for resilience. Because yeah, that's
in fact, it was introduced I think, by Netflix that use it a lot. In the enterprise, and one of the ultimate, maybe they do things even bigger. But at some point, there are many data centers. They intentionally shut down one data center to see what happened. It was in production. The clients were connected and so on and so forth. So it's really the idea to introduce errors in the distributed system while it is really used by clients. Yeah, exactly. Yeah, and that solution that you mentioned is named Chaos Monkey, because they assume that they have a monkey, and the monkey is unplugging the servers, unplugging the routers, switches, and it's supposed. Also, you quoted at the beginning. I think she was working.
Yeah, she was. Yeah, Aaron was working initially. Yeah, in Chaos Monkey, exactly. Yeah, that's the history of the project.
So I go on the discuss about the people. I mean, there were people checking on the time. I mean, they would listen to the keyboard noise to try to infer things and check whether encryption was. And so people also do things on the fly, right? Not just at the inception of the system, right? And so people look at the scenarios and they find new attacks, which are when the thing is deployed or and used, right? Yeah. So okay. Yeah. The difference maybe I always say that is okay. You implement some security controls, for example, in the case of Netflix, that allow you to affirm that the solution will works. For example, for the user will not realize that some servers are not working. The user will have an excellent experience. That's the promise, that they will have an excellent customer experience when they are looking at
broadcasting videos and different content. So if that's the promise and Netflix it's pursuing that goal, they will validate if that's true. So they will not wait until a situation where the user has to experience that kind of situation, but they will provoke. They will introduce the situation in advance so they can validate if they are able to do it, if they are able to support, because they have security controls, load balancers, resilient systems, duplicate systems that should be able to keep the system working, even if a monkey disconnect or unplug some kind of system. Yeah, that's the basic idea. In this case, it's the same. I mean, we implement some security controls, so we introduce the fails to validate if the security controls are working or will work in the case of a real attack. That is. So yeah, our first goal after we started studying security chaos engineering was to implement a security chaos engineering solution. Say, okay, that's good. The theory is good, but we need to implement it. We need to validate if this actually works or not. So we wanted to implement a solution that could be used to identify vulnerabilities in software. That's the solution. The first solution that we proposed was named Chaos Exploit. It's not a very original name. I mean, it's the union joining chaos and exploit, because it's using chaos engineering to exploit software or to exploit vulnerabilities. But this was our first proposal. And we will use, in this case, attack trees. The attack trees actually are the logic or contain the logics behind the attacks. Okay, so yeah, this was our first proposal. So I will speak a bit about it. This was a framework based on security chaos engineering using attack trees. I will show you later how an attack tree looks like. It's interesting. And using, of course, the methodology that I explained before, with the aim of identifying vulnerabilities in infrastructure. In this case, only infrastructure. I will speak later about an example that is applied in the application layer, but in this case, we will speak about cloud infrastructure, specifically cloud infrastructure. So this tool, Cloud Exploit, is available in a repository, in a public repository. Everyone can download and install the software and use it, of course. There's no problem. This is the architecture of Cloud Exploit. So I will try to explain this in a simple way. We have 3 different layers, and you will realize that in these layers of the architecture is the security chaos methodology. Is embedded. It's in the models is the same methodology. So in the first layer, we have the observer. In the observer, we do the first step of the methodology. So the first step, as you can see there in the corner, is identify the steady state. So we identify what we want to measure, what we want to observe. We want to observe in the system the parameters of network, or we want to observe, for example, the policies, or we want to analyze or to observe the behavior of the user. What you want to observe, you have to define that in the steady state. That's the first step. And of course, we have a continuous validator that validates that keeps running as supposed to do. Okay. We have also a second layer that is the runner. This actually is the one that does the exploitation. This does the exploitation, and this has the logic. This is the brain behind the exploitation of the vulnerability. We name this exploiter. Actually, it's the brain, the exploiter. And then we have the logic. The logic are the attack trees that contains the steps that we have to follow to do the attack. So we name this the knowledge database, and we have different attacks for different kind of targets. So we have attack trees for applications, but attack trees also, for example, for cloud services, for Kubernetes, and also for network. So this means that we can use this same proposal, this same methodology at different layers. That's what I respond to Joaquin, that is not specific for one layer, but can be applied in different layers, because depends on the attack trees that you have. If you have attack trees for a different layer, you can use it that, and yeah, it's not bonded by a specific layer. So yeah, this was our proposal of architecture. We implement this, and this is I will explain now about one of these attack trees. I will explain this specifically, the cloud service tree or cloud service attack tree. That is this one. This one was an attack tree specifically for a solution that was tested in a cloud environment. So we have you know, the S3 buckets, that is the storage solution of Amazon. So there are different kind of buckets. We have a bunch of buckets, and the 45% of those buckets can have some misconfiguration. So we wanted to validate what was going on with those buckets that were misconfigured, if they are exploitable or not, and what was the procedure to do the exploitation. So we wanted to validate that. So using, of course, the Cloud exploit that we implemented before. So we define different attack trees. And here, the interesting thing here is that the attack tree is not used to define the steps of the attack, but it used also to define how the attacker will think. So the attacker will try the option that offer the less effort. The attacker will not try, for example, to break a cryptographic system that is very strong. It will try to break the cryptographic system that has vulnerabilities. So what we have here is the concept of ROI, the return of investment. So in the left branch, we have the return of investment number 1, return of investment number 2, number 3, and number 4. The idea here is that in the mind of the attacker will try to use the branch that represent the less effort for him or for her. Okay, and in this case, for example, this attack tree is developed using that mentality. So we have in the branch number 1, for example, the easiest option for the attacker. The attacker, what will do? Just find public bucket. I don't want to focus in a specific bucket of a company, but only find public buckets, any public bucket that is available. So I will go for the first option. I will validate if they are active, if they are online. So I will check possible connections. That's the second step of the attack. Then I will validate if they are collectible, because some of them are public but not collectible. So I validate that it's collectible, and then I will review the access control list so I can identify if I have or not the permissions, and then of course I will exploit the permissions. So at the end, for example, here I have every attack tree has an attack goal. The attack goal is the maximum goal that is always in the bottom of the tree. So you will see different attack trees in this presentation, but all of them have more or less the same structure. Different branches. The branch in the left is the easiest branch. The left and the right is the hardest branch. It's the one that the attacker probably will do, but if there is a very good benefit, a very good reason to do it, because will imply, of course, a bigger effort. And also at the end of the attack tree, there is always an attack goal. The attack goal will be the final objective of the attack tree. So in this case, this is the attack tree for this scenario. This is specifically based in misconfigurations in cloud computing. And then here we have the results. There is results we are already implementing the experimentation here using Chaos Exploit, the tool that we developed before. And here, okay, we define different conditions. For example, here, first, we define observability. Okay, if we will measure the quality of the configuration of the security configuration of S3 buckets in Amazon, we will validate, for example, if they are accessible. So the observability will be the accessibility property of the buckets. Then we will validate the steady state, or we will define actually the steady state. The steady state says to us that the buckets, if the buckets are properly configured, they should prevent unauthorized access. That's supposed to do. We don't know. We will validate if that's true. And then in the hypothesis, we will validate, of course, in this case, if someone tried to access to the bucket, he or she will not be able to access the bucket if the configurations are properly configured. We will validate this, and the Chaos exploit is configured to do that validation. Here we have the proofs where we are reviewing each bucket, each public bucket, validating the permissions that are being obtained, and then, as you will see, we found some buckets that are public. Yeah.
For this experiment, are there any deployed in real cloud?
Yeah. Actually, these are real buckets. Yeah, we found. You will be surprised.
So how did you process those? So they are cloud from Amazon.
Yeah.
So you have some agreement with them. It's a collaboration.
We just find we use a tool that find public buckets in internet from companies, from everyone. every company that has a bucket that's not configured properly.
My question is, then you are an attacker. So
we were reviewing. You were reviewing the public buckets that were available, and not attacking actually because we were not allowed. Yeah, we were not allowed. We just did a review of the buckets that are public. We found 3,000 buckets, for example, that were public, and yeah, that the bucket.
So you do not go. So to close.
Yeah.
This point of discussion, you do not go up to the real attack. You just try to find what could be attacked.
Exactly.
And then
exactly. Yeah, because we don't have any contact with the companies that are behind this bucket, and we will not be allowed.
You also for them to a way to test the vulnerability of the cloud.
Yeah.
Then you need
yeah, exactly. We go to the point that we are able to validate that the attack will be possible, and yeah, but we didn't.
Because then did you tell them? What did you do with them when you discover some vulnerabilities?
We discovered that the buckets are available. We discovered that the permissions are available and that are readable, and the objects are downloadable. And after that, yeah, we could depend on the company and depend, of course, of the Amazon policies also. But the next step is to report that. But yeah, it's a typical preventive countermeasure. But even you will find companies that they don't even reply the message that you were saying.
Okay.
Yeah. So yeah, we found 3,000 buckets. Actually, we found 3,000 public buckets, and from those buckets, for example, some of them, when we try to connect to them, some of them refuse the connection to 271, refuse the connection, and 2070 more or less they were connected. And from those ones that were connected, there are different categories. Some of them, they deny the access. I mean, they are alive, but they deny the access. They are public, but they deny the access. Some of them allow the collection of objects, for example, in this case, 252. And then also some of them allow the ACL collectibles. The ACL policies, sorry. The ACL are the access control policies that are configured in the bucket. So, of course, the most interesting are the ones that are here in this intersection between the two groups, because those are collectible in terms of objects, but also collectible in terms of permissions, both of them. And different kind of objects, of course. We validate just without downloading the object, but just reviewing the characteristics and the metadata of the repository, you can validate all of the objects that are there. In most cases, image, PDFs, documents, different kind of public objects that are in those buckets. It's interesting, for example, to identify here that, as I mentioned before, that 69 buckets were collectible in terms of objects, but also in terms of permissions. And in this case, one of them, for example, allow you to validate who has the full access control. This is quite dangerous, actually, because you can identify one vulnerable account that has full access control, attack that account, and then gain the access to the bucket. Okay, so this is an example of the application of security chaos engineering. We start from observability, we define a steady state, we assume that the security control is properly configured, and we validate that it's not. So we refuse the hypothesis. Okay, who could use this kind of solutions or this kinds of techniques? Well, there are different kind of agencies. Yeah, tell me. Yeah, sure.
So I just wondered if you implemented one type of attacks, and chaos exploits surely has other type of attacks, right? So I wondered, how did you build the models? Is it based on real attacks, or did you build them on the implementation? And second question is, at what level are you exactly? Are you on the Cisco level, or are you HTTP, and how did you choose your level of
Yeah, sure. Thank you. Well, I will say here, this kind of attacks are you can propose that branch of the attack tree, but you will also find different web pages where the attacks are documented. For example, hack trick. If you look for hack trick in Amazon, or it also can be applied to Azure or to GCP, you will find different procedures similar to the Mitre attack matrix where you can find the different steps that you have to follow to do one specific attack. So that procedure can be taken from the matrix and put in the form of a tree. Yeah. Also, of course, you can propose some attacks that are different from the matrix, but yeah, it's that source. You can use documented attacks or new attacks that you think that are that have some that make sense in the concept in the context that you are testing. For example, in this case, what we are doing is actually this one. We just for the purpose of showing a use case, a simple use case, we are following the first branch. That is the simplest branch.
So you create this tree backends for each type of person.
Yeah. And I will speak later that we are working right now and generating automatically the attack tree using LLM, like ChatGPT and that one, because you can, of course, use start thinking about, okay, what happens if I provide the context, I provide the assets, the digital assets, if I provide the topology that is behind to a model like LLM, and okay, could he be able, or could it be able to propose some kind of attack? Probably some kind of. We are working specifically in that direction. Yeah. And the second question, could you
Level of.
okay, the level. This is, I will say middleware. It's not application because it's not end user applications, because if in Amazon, all of this is running in the middleware, the configuration of the buckets, configuration of policies, configuration of the IAM, all the modules, the software modules that Amazon gives you to do the deployments. So it's software, it's in the layer of software, but not software of end user, but software for administrators. It's software that is used by the administrator of a company that do the setup of the buckets or the infrastructure that is being consumed in the company. Sorry? No, it's not. I mentioned middleware. Middleware, that is is the term that we use to indicate that it's not the software, but it's behind the software. Yeah, and the protocol. Yeah, in this case, there are different protocols. For example, we use HTTPS. Of course, it's Sage. The most of the cases in this case are validating the connection to the buckets using simple HTTPS. I mean, all of them are connection. HTTPS requests validating the bucket, if the bucket is alive, if the bucket is collectible, and then analyze the response. Yeah, it's an application protocol, let's say. Yeah, sure.
Are you supposing that you have an S3 service account within Amazon in which you can start this kind of attacks, or are you imagining that you start the attack from your laptop outside of the S3 service? Is there any difference actually?
Yeah, in this case, as we decide to follow the first branch, we are not focusing on a specific target, but in any organization that has that vulnerability, not in a specific one. But if you want, for example, to make to be more focused in a specific organization, maybe the first branch is not the proper one. Maybe the second branch would be the proper one, because the second one, for example, the third one are specifically for one organization. So in this case that we are showing here, it's more general. I mean, it's not as business focused, but it's more any other business that has the vulnerability. That's the goal in the first branch. Yeah, but depend on the attack that you are pursuing. If you are doing, for example, a review of vulnerabilities in the cloud computing deployment of a specific company, you have to, in this case, for example, identify user account permissions for that organization. And with that user account permissions, try to identify, for example, if there is an AIM policy that is not configured properly. So depending of the context, probably you will take the branch number 1, or you can go directly to the branch number 2. The attacker will try, of course, to do them in this order. First the one, then the second one. If the second one is not possible, then the third one, and then the effort will increase to the right.
But you assume that this classification is actually provided by yourself, right?
Yeah, this attack tree is was built by us. Yeah.
Okay.
Yeah.
In this regard, the basic, how do you know that this is easier than this for example, phishing maybe to me, I don't know, is easier than brute force user's credential. I don't know which criteria or.
Yeah, in this case, for example, it's only based on the technical effort behind each this kind of step, because as you can suppose the phishing could be uncertain, I will say, because depend of the awareness, the cybersecurity awareness of the people working in the company. If you have, but that's something that it's not, it's out of the scope of the ethical hacker or the hacker mentality, because it doesn't have a way to, it's not, it doesn't have the guarantee that using phishing will be allowed to exploit the fourth branch. Yeah, in this case, it's only based on the effort behind the attacks, the technical attacks, not the social engineering or the hybrid attack.
But for sure, sorry.
No, it's okay.
For this point, for sure, when you classify things according to this representation, and at the end, I suppose that you have some advices to Amazon, right? And your advices will be for sure based on this kind of classification. But what will happen if Amazon is not seeing things in the same manner than you?
Yeah,
if he's giving more attention to one of services or part of services in which you would like to put more security, for example. Yeah,
what we have realized, for example, is that Amazon is doing some kind of is implementing some security after these branches are attacked. So, for example, they don't allow you anymore to put by default a public bucket. They force you to put a private bucket, and you can also put the public bucket, but it's not the default option. I mean, you have to disable the configuration, the secure configuration that came by default. So they are doing efforts to avoid that these branches can be attacked. Yeah, and I will show you, because I will show you later how an attack tree looks like when you implement the countermeasures, because these steps are only a step of the attack. But what happens, for example, if I implement the countermeasures? So I will have one branch that maybe is detained here by a countermeasure, another second part of the branch, and then maybe a third part of the branch. So you can have a defense in depth concept, for example, when you have one security control that is bypassed, then an attack procedure, then a second control that maybe is also bypassed, and then a third one. So you can see the defense in depth architecture actually in terms of controls that are implemented in the middle of the branch. Yeah, I will explain later in a figure how that will look like. Okay, so this solution can be used, and actually is being used as is for resilience, for site reliability, but of course there is also the idea of implementing this in cybersecurity solutions, not only in site reliability engineering, but also in cybersecurity engineering. Okay, we present this proposal in two different scenarios. First, the Spanish Conference of Cybersecurity Research, that was the last year in Bilbao, and we published also a paper in a journal named Big Data and Connected Computing, showing this proposal. So, okay, just to do a checkpoint before continuing to the next proposal, what we have learned until now. Okay, we learned about what is chaos engineering. Maybe some of you didn't hear this before, but this was a first opportunity to know about what means chaos engineering, what means security chaos engineering, that is the same chaos engineering but applied to security. We learn also about the methodology behind, because it has a methodology. What we also learn about a new tool that is Chaos Exploit. It's open source. You can use this if you want. And we also learn about a use case, a simple use case based in misconfiguration of buckets in Amazon. But it's a use case that allows us to see how this can be applied. Okay, so that's what we have learned to know. So what was the next step that we were thinking about? We were thinking about how to use this chaos exploit in different scenarios, for example, in military systems, because we were thinking about an application specifically for the military sector, and also in IoT systems, IoT solutions. That's what we was playing know in a use case, in a new use case. And also, we are thinking about something that you mentioned before. That is, okay, not only attack, but if the attack tree allow you also to discover the countermeasure that you will put in the branch to avoid that the attacker go in the next step, then the next step, that will be nice, because you will you can decide to cut the branch. If you cut the branch, even with a simple step, you will avoid that the attack continue going down through the branch and then go to the attack goal. So that's what we are working also on. We're also working on. So we're thinking, okay, working in the security of Amazon is okay, but what if we go a big upper to the software level? So we'll start thinking about the problem of the secure software development lifecycle. We have here some statistics about in US, for example, we have a very big problem where there are a lot of millions of dollars that are spent in cybersecurity fails related with software. Most of them are because the secure software development lifecycle is not implemented. It's not properly implemented. They don't have the proper testing, or they don't have. They have a deployment, but it's not the best deployment. So it's a lot of money that is being spent, and of course that means that the traditional techniques are not working on. If the traditional techniques will work as supposed to work, maybe we will not have this kind of problem. So we need actually a new techniques. So we try to implement or to integrate actually the chaos engineering with a new concept, related with AI, natural language processing specifically. Okay, what will happen if we provide some input to the attack tree that is the output of a natural language processing model? That will be nice and will be useful to avoid the manual work. And what new methodology for securing software we could be used? That's the security chaos engineering methodology. So we do a second proposal. This is the second proposal that we developed, that is the integration of security chaos engineering with natural language processing to improve or enhance the secure software development life cycle. And in this case, yeah, we implement another architecture that contains the chaos exploit, like the heart of the solution, but also additional modules that give more functionality. So the system was applied, as I said before, to a cloud-based military system. In this case, could be applied to the supply chain problem in the military field, but also could be applied or is applied to IoT solutions or IoT devices that are deployed in a field. For example, in this case, we know, for example, from the case of Russia and Ukraine war, that we know that there are different drones and different IoT devices that are controlled remotely, and they are operating in the field, in the war field. So those IoT devices actually are smart devices. I mean, they are smart at all. So yeah, that's what we are trying to identify. Okay, the information that we are collecting from an IoT device that is deployed in a warfare. Okay, so we do a second proposal, and this second proposal, as you see here, I will put this box up so we can see the full picture. We have here the chaos exploit, as I explained before. The chaos exploit has an attack tree that is a knowledge database that contains all the logic of the attacks. Good. Also have the attack tree generator. That is the one that composes the attack tree, but we have some additional models that are novel. So the new models are, for example, this one here, that is a name entity recognition model. If some of you have studied natural language processing, this is a really powerful model. There are different really powerful models that can be used to identify the entities, for example, in software requirements. So we are using that model here. And also we are using a second new model that is the threat modeler. The threat modeler gives us different threats that are identified in cloud infrastructure. So we can be able to identify also countermeasures. So yeah, this is the architecture. We have, for example, the functional requirements that are the input for the NERD module. The NERD module give us the key entities, and in the second part, there in the right, we have the topology where the system is being deployed, and in that topology is the input for the threat modeler. The threat modeler gives us the threats and the countermeasures. So in the center, we have the heart, that is this chaos exploit that's receiving the inputs from the left, that are the key entities of the requirements, the software requirements. And from the right, we have another input that are the threats and the countermeasures that are being analyzed by the threat model generator. So at the end, it's interesting because we were not thinking about this at the beginning of the research, but we have now something that is chaos engineering being powered by natural language processing that is helping to analyze the security software requirement, the use case, the stories, the user stories, and also is powered by a threat model generator. I will explain these models now. Okay, so the natural language processing allows us to recognize the actors, the actions, the privacy, personal information. This allows us to validate what's important in the system, because our idea is that the chaos exploit depend the less as possible from humans and can be more automatic, more independent, more autonomous. So yeah, if the model allows to identify the most critical assets, that's good. So that's why we integrate this model. And also the second one to identify the threats and to compose the attack tree. So we have different technical tactics and procedures that are being used by the chaos exploit to do the attack tree. I will show you this solution. Okay, so we have here a very simple figure that contains some modules in a military system. So we have different levels. We have a soldier that is in the operative labors, let's say. We have a supply manager that's more tactical activities, and we have a commanding officer that is more strategic. Yeah, and we have also a cloud-based system that is implementing an IoT solution that is receiving information from the battlefield and is giving some kind of reports to these users. So these are the use cases. The use case, for example, we have a logistic officer that want to guarantee that any IoT device, imagine a drone or imagine some kind of sensor that is deployed in the warfield, trying to monitor or measure some kind of parameter and reporting that value to the center commanding. And then we want that the logistic officer is interested that the report can be done properly. We also have a supply manager that's interested in getting information. He is not interested about the reporting, doing the reporting, but of getting the reporting. He wants to know the information of the IoT devices that are distributed in different locations. And then we have the commanding officer that wants to generate a strategic report and to validate, for example, in this case, a supply chain performance based on the IoT devices. So this solution is a very complex solution, actually. Here looks maybe simple, but it's complex because it's based on cloud. We have different IoT devices, different front-end servers, middleware servers, application servers, and databases, and different kind of users with roles and permissions. So this is deployed in the cloud. Actually, Amazon has a specific cloud for the military sector. Only can be used by the Department of Defense in the US. And here, for example, we will see the model running. So first, the natural language processing model identify the actors, the actions, and the personal identifiable information here with different colors. The model does this automatically. I don't have to do anything. The model identifies who is the user, what I want to do, and what's the object of the action. So this is actually quite good, has very good accuracy. And we use also another tool that is a Spanish solution from a company that is Irius Risk. Irius Risk is a threat modeler. So you put the topology of the solution that you want in Irius Risk, and Irius Risk identify the threats and identify the countermeasures that you should deploy. say, suggest some countermeasures. So it's good. It's a good threat model left solution to identify these kind of vulnerabilities and countermeasures that should be deployed in a topology. So here, for example, we say, okay, that solution that we mentioned before has different cloud services, cloud services that are AWS CloudFront, WAF, Lambda, EC2, well, all of them that you see there. So what EDUs help us is to identify, for example, this kind of threats. Say, okay, for example, yeah, the attackers could abuse the functionality of the server to read or the internal resources, or, for example, the Lambda function of the cloud solution could be compromised with a code injection attack, or, for example, the data in the S3 buckets could be encrypted, for example, in a ransomware attack, or could be deleted also intentionally or accidentally. Okay, or for example, here in the EC2 instance, could be maybe there is an unauthorized access to the instance. So are generic attacks, but those attacks are for this kind of services in cloud. And with the information, this slide maybe is quite important in this second use case, because here we integrate the actors, the actions, and the targets that are obtained from the natural language processing model with the threats and the countermeasures from the EDUs tree, that is the threat modeler. And we integrate all of that in this attack tree. So we have here different colors, and this is the answer for your question. We have here in the light blue square, we have the attack, and the dark blue we have the countermeasures. So we have different branches. All of them have different ROI, different return of investment. But the situation here is that, for example, if we use the left one, we deploy one control, the control that is there. If that control fails, the attacker will do these steps. And then we find another control. If this control also fails, that is the second layer of defense of the solutions in a defense in-depth architecture, then the attacker will achieve this attack goal. So here we have a more complex attack tree where we have different controls, one followed from another one. We have different vulnerabilities, different kind of attacks. And these are real attacks. If you look, for example, for real attacks in Amazon, they are documented in attack tree. In hack tree, sorry. In hack tree, you will find the steps that are here. It's not, it's not science fiction. It's real. These attacks really work and can be reproduced in Amazon, for example. That is the environment that we are using now. So yeah, what we wanted to do is to validate. Having this attack tree, we wanted to validate that chaos engineering, of course, help us to build the tree, but also to validate if these vulnerabilities exist in the solution. Yeah.
But this graph has been automatically developed or has been developed partially by you, or?
Yeah, this was completely generated by us, and we are, because we are like increasing the complexity. First, it was only with attack steps. Then we have attack steps, countermeasure steps, and we also have the business assets that are embedded in the attack tree. And then the next step that we are working on is to generate it automatically. I mean, we want, as I said before, we are working on doing the attack tree the most autonomous as possible. So yeah, it's what we are working, and natural language processing particularly is quite useful to do this kind of proposals. But yeah, we are increasing the complexity gradually. Yeah, sure.
Maybe just to complete the question by using two people on the tree. Could you just explain why the countermeasure is coming somehow in the first column of your graph too late? Is it what's really your choice to put this countermeasure just before the target? Could we put it before maybe?
Yeah.
What was your criteria you used to, let's say, to decide to put it right there and not before?
Yeah, I thank you for that question. That's a very good question. It's not a stupid one. It's a very good one. Actually, you know that there are different kinds of security controls. Some of them, they are preventive. Another one are corrective. right? There are another one that are deterrent, that they avoid that attack can be done. Another one are post-mortem. They are named post-mortem after the attack. Okay, so what we are doing here actually with the first control is something that is prevented. I have a Lambda function that has been deployed. It's supposed that it's secure. I don't know if it's secure. That's what that I will validate using chaos engineering. I suppose it is a secure Lambda function. So that was a preventive control because I implement before the attack. But this one here is post-mortem. War duty is a solution that is able to detect and has some kind of properties to correct, to remediate. So that's why this is after, because this is specifically war duty is a specific solution that allow you to detect anomalies and also to do some kind of remediation, kind of automatic, because you can develop some kind of Python scripts to do an assurance immediately after some anomaly is detected. So that's what it is before, because in the timeline of the attack, you have to first prevent, and then after the attack is running or is being detected, you have to do the remediation. Thank you for thanks. Okay, sorry, okay, 5, sure, I will. So in this case, we didn't want to implement the easiest branch. We wanted to be a bit more confident implementing a harder. So we implemented the first branch, okay, the one that is more complex. So we implement that one that allows us to do a privilege escalation in an instance to obtain information that is being reported, for example, for IoT devices that are deployed in a war field. So we wanted to validate if a solution deployed in cloud is protected against privilege escalation that allow, for example, that somebody, an attacker could obtain information that is reported by the IoT devices or by the logistic officer or the supplier manager officer. So we implement different experiments. Here there are 4 experiments. All of these experiments are using the chaos engineering methodology. We have the hypotheses, what we want, what we will observe, what we will measure, what will be tested. This is the experiment that we implement. As I said before, we were focused specifically in the branch number 3, not the easiest, but one of the most difficult branches. And then we implement all of the solution following here the configuration. So first, we implement the security policy We assume that the security that the policy is secure. We will validate that using critical engineering. We did the attacks that are supposed. We did enumerations, and we steal the profile credentials. And the things here is, okay, if you are able to steal the credentials, something should be deployed in the Amazon solutions that avoid you to use that steal credentials. Something should detect that you are using credentials that are not from you. Something should exist. What's that? War duty. War duty, if it's correctly implemented, should detect that you are using credentials that are not assigned to you. So in case that this security control doesn't work properly, the privilege escalation will be possible. So what we did using chaos engineering was to validate what we assume that will work by default. We assume that this will work, but as you see here, that is not always the case. And also we assume that the war duty will detect and we correct the attack, but it's not the case, okay? So I will show you, as my time is running out, I will show you the results. Let me show you here the results. Here are the results. So we have here the first step of the methodology applied to this scenario when we have a steady state validation. When we have the scenario that we want to observe, that we want to implement, we assume that this state is a normal condition. The normal condition, I will not be able to do a privilege escalation. In the second scenario, I create an instance. That instance that I create will be the victim instance, okay? And then I connect to the victim instance and I steal the credentials. And after stealing the credentials, I use the credentials that I just steal to execute another AIM commands. So this is the the console of Chaos exploit. It's not a nice or fancy interface. It's just a command line. But yeah, we also want to improve the graphical interface. But it's quite simple and it's quite easier to see that actually the credentials are being obtained. You have here the credential extraction. This is also obtained from Chaos exploit, and then actually we obtain here that if you have the WarDuty properly configured, WarDuty will detect that. It's quite smart actually, because detect that the credentials that were assigned to an instance, to an EC2 instance, are being used by another one, by another user. So we have here the detective control. This is the detection. This is detection. And in that case, for example, yeah, the attack goal was not possible. So the hypothesis that this works is confirmed. So this is this is being used and is being evaluated, for example, by Indra, that is a multinational company that is working in cybersecurity and cyber defense specifically, because they suppose that they want to implement these kind of solutions for the services and the products that they are selling. Okay, and yeah, for finishing the presentation, yeah, what we have seen before is that we will integrate security chaos engineering with natural language processing to give more abilities, I will say, in the detection of vulnerabilities, not traditional vulnerabilities, but new vulnerabilities that are not being detected by traditional techniques. We also introduce in the second part 4 modules that are quite interesting. For example, the threat modeler, that is, as I mentioned before, using a module that a software solution that is Irius Risk. Also, we introduced the attack tree compositor, that is the one that built the attack tree by itself. And also, we are extending, as I said before, in the automatic composition of all the logic, because we are, yeah, increasing the complexity to the attack scenario to make it more autonomous as possible. Yeah, and yeah, that will be that will be the end. Thank you so much.
There were a lot of questions during the talk. It's good.
Yeah.
So we are time for one of question. So first I will ask online. Are there some questions online in the room?
Wondering if the guys online are not here in the room, because I think we are.
So is there some question in the room?
Yeah. I have a quick one, but maybe we'll discuss this offline. Just to don't forget about us previous question. So you mentioned all time attack trace, and I was wondering if you consider also attack graphs from the point of view of automating the process using expert systems that automatically generate the attack graphs.
Yeah.
But like I say, maybe to discuss offline and to don't forget this question.
Sure. Yeah, we can talk about it a lot because yeah, that's one of the things that we are taking also to improve, because yeah, attack trees have some benefits but also some drawbacks, and so yeah, that's one. Yeah, it's something that we are also thinking about implementing. The situation is that there is not many solutions around security chaos engineering. I mean, there is one proposal from a German university, another one, a British one, and our proposal. So there is not a lot of a lot of solutions in the state of the art. So, and the solutions that are implementing till now are more based in resilience than in security. So yeah, that's something that we would like to implement, to add to the solution. Yeah, that's a good future one. Yeah, sure.
Could security chaos engineering be used to do differential comparison between binaries or program? Like this part of a differential comparison, is it something that can like make sense?
Like compare?
Yeah, can we compare also dynamically? I know several programs, because here we are all the time focused on one target.
Mm-hmm.
We are not doing differential on production.
Yeah, the comparative. I think I understood your question. You will tell me later. the comparison with this technique and other techniques depend on the quantity and quality of the vulnerabilities that are found. If with additional techniques you find some vulnerabilities that are great, yeah, but those vulnerabilities are always the same and different from the ones that you are finding using security chaos engineering, then in that case, that differential, the new vulnerabilities that you find are actually the benefit, because yeah, you don't want that somebody tell you vulnerabilities that you already know. But if somebody tells you vulnerabilities that you didn't know that are really novel, that's the benefit. I mean, that's the interesting point of applying security chaos engineering. So in terms of comparison with traditional techniques, is the base of quantity and quality of vulnerabilities that are found in the application of the methodology. I don't know if I found a question.
I guess I was thinking about there's something that's called differential testing. So it's when you first try programs and see differences. And I wondered if there is something like differential security chaos engineering. But I guess no.
No, there is not. Yeah, there are. Yeah, as I mentioned before, there are only like three solutions. Chaos Monkey is not being developed anymore. It's not under maintenance, unfortunately. So there are some solutions. There is some company actually. The guy who started with the concept of security chaos engineering, Aaron Reinhardt, he created his company. And he's offering this. He's the only company in the world that is offering chaos engineering for detection vulnerabilities. So in this moment, he doesn't have competence. But it would be a good idea, actually, to implement solutions. I mean, we are more in the research area, in the academic area. But if somebody is one of our students or alumni would like to take this idea and implement a service, maybe by sure we'll do a good different services in the industry, because there is not organizations that provide this kind of solutions. The most of the organizations that you will find are the typical ethical hacking, typical testing, without a methodology, a specific methodology. It's more the methodology that the ethical hacker has in his brain. But if you find as something like this, that with a methodology that find new vulnerabilities that are not discovered, that will be a good differential.
What I propose is to stop there. Is there other
Sure.
questions? You can have questions offline.
Yeah.
Thank you again.
Thank you so much.